So let's talk about moving from set of charges to a scenario wherein we have two charges and they are opposite in nature but equal in magnitude. That is, we're talking about dipole. So let's see what happens when we keep a dipole in, of course, uniform electrical field. We are starting off with a simple scenario. So we have a uniform electrical field and we are placing a dipole. So we have, say, the positive over there and the negative over here. So we have the line that joins these two, and this is the angle. So there is a push and there is a pull. The push and the pull are equal in terms of magnitude, but opposite in direction. This entire length is 2a, and we need to talk about the moment, dipole moment. It would be from negative charge to positive charge, and so on and so forth. Now, if we have two things which are pulling in this manner, what happens? Yes, it leads to it not going anywhere, but it will rotate. Common sense. If you take up a sheet of paper or a book, if you guys pull it in this particular direction, just point out your fingers, or you can do the other way around, just push it in this set of direction. What happens? It will rotate but not go anywhere, because the amount of push and the pull will be the same. What happens? Nothing happens. Tug of war. If both the teams are equally strong, what happens? Nothing happens. But here again, I'm repeating myself, it will lead to a rotational motion. So we have the write-up telling that the charge Q will experience the force of EQ and minus Q experiences the force of minus EQ. Since the field is uniform, the strength has to be same, and so the resulting force is 0. There's no translation motion. Agree? Now, but there is rotational motion. Dipole still experiences a turning effect, and the turning effect is force into perpendicular distance. So let's have a look at this. We need to figure out the perpendicular distance. I'm just doing that. So this length is 2a. What else do we know? That, let's say, just a second. This, not that. This and this creates a correct right angle triangle. This is angle theta. So what is this length? 2a cos theta, right? Nope, this is 2a sin theta. Opposite side, opposite to angle theta. So why is that I'm taking this, not this? Because your direction of force is to the left and right, and the perpendicular distance between the couple is 2a sin theta, not 2a cos theta. Again, you have the force in this way. This is your perpendicular distance, is it not? Think of it. Take a second. You should be very clear with why we are taking 2a sin theta, not 2a cos theta. This length is going to tell how far away horizontally this forces are. It won't help us. It won't help us in rotational stuff. What helps us is this length. Agree? So your force is EQ, EQ. So finally, your torque because of the couple will be the force EQ and the perpendicular distance. But 2AQ, what does it form? Yes, your dipole moment. Now, if the dipole is rotated through a small angle d theta, so we are doing work on it, we are rotating it. What happens? Well, the work will be equal to force into displacement, and this will be equal to EP sin theta d theta. Of course, we don't generally do small work. We do a lot of work. To add all of them, what should we do? Yes, integrate. So theta I to theta f, all the work between that. Remember, we are rotating. So when we substitute this, it's quite simple. EP uniform, P is constant, E is uniform, so that's also fixed. Sine theta d theta is what we have to integrate. And integration of sine theta is correct. Tan theta. Is it not? Nope. It is minus cos theta. Okay, guys. And so we have minus EP. Right? You know this is definite integral, so we can ignore the constant. So theta final minus theta initial. Remember, I have the negative out. If I put it in, it will flip. Okay, yes. So don't get confused. So one of the negative is over here. You might find a different expression in your books, so don't get confused. It's the same. Math is the same. Of course, this is not our final expression. We have one more thing. We always talk about any kind of energy gain or loss with respect to some reference line, some kind of zero. In this case, 0 is 90 degree. We have seen all of this. We have seen the dipole. We have seen how it behaves and all of that. Right? So we always have a reference line to which we consider, from which we consider the energy gain and loss and so on and so forth. So here too, we have our 0 at 90 degree, right? Because we have this to be cos of 90 degree. Now, let's consider dipole if oriented perpendicular to the direction of, theta I is equal to 90 degree. It has 0 potential. If the dipole is moved by an angle or to an angle of theta, then the potential dipole will be simple. Actually, I don't know if I read it right. Minus EP, this will be cos theta minus cos of 90 degree. This is nothing but 0, and we have minus EP cos of theta. That's it. That's your expression. Okay, yes. And by the way, all of this is nothing but your energy. The system will gain this much of energy. I kept writing W, right? So this is also your potential energy. Okay, so that's done. So we are looking at a special case wherein we have a position of stable equilibrium. How or what place should we keep this dipole in this uniform electrical field so that it's in stable equilibrium. So I hope you guys remember the definition of stable equilibrium. A small displacement, the system comes back to its original scenario. Again, you guys have to be very good with your basics for understanding your 12th grade, higher grades basically. I need a diagram, so I'll make use of this scenario. This space, not scenario. So we have the dipole, and say we have the electrical field in this direction. Now, say this is positive Q and say this is negative Q. What happens? This will get pushed to the right and this is to the left, right? Nope. This will get pushed to the right and that is going to get pulled to the left. Nope. This I'm wrong. What I told initially was right. Now, if I displace this a bit to the left and right, so on and so forth. Either ways. Now what happens? This is your case 1. So in this case, the forces are equal and opposite, so nothing happens. In this case, what happens? There is a pull to the left and this is push to the left and pull to the left. My bad. Push to the right, pull to the left. And they are making an angle. The perpendicular distance exists. And so what happens? It has to rotate. How will it rotate? It will rotate in this direction for this particular scenario. So is it going back to the original state? No. So this is unstable. So what will be stable? Stable will be that we have the positive to the right and negative to the left. Agree? So let me do that over here. We'll come back to the unstable scenario. So we have the negative over here and positive over there. And when we displace this, what happens? The turning effect will be such that it will snap them back. It will push them back. So what is the angle now? Well, the angle between your electrical field and your dipole moment is one and the same. So basically theta is equal to 0 degree. Agree guys? Think about it. It should be 0 degree. So that would be your answer. Does it make sense? So that's the position of your stable equilibrium. Position of zero energy is theta is equal to 90 degree, right? Reason being U minus EP cos theta will be equal to 0 joule for theta is equal to 90 degree. As simple as that. Now, what about unstable equilibrium? So, this is a case of unstable equilibrium. But what is the angle? I need to teach you guys how to read the angle. I'm sure you guys remember, but still, let me revise, right? It will just help you gain the confidence. So here we kept your positive, here you kept your negative. So from negative to positive is your dipole moment, while your electrical field was to the right. In our above diagram, that is. So what is the angle? They are anti-parallel, so this is 180 degree. So that's the point of your correct unstable equilibrium. So to conclude, the potential energy of a dipole is maximum when its dipole momentum is correct parallel to external electrical field. No, yeah, you guys are right. I know I should not be doing this repeatedly, but yes. And finally, we can put up energy versus angle graph. Just a minute. Actually, I think I have it. No, I don't have it here. Let me put it up. It'll be faster. Yeah, energy versus angle graph. What is that we're looking at? This is the angle and this is the potential energy the system will gain. Now, if I keep the angle at 0 or 180 degree, what happens? Look at that. I think the graph, just a second, let me have a look. Oh yeah, it's right. So this is our 180 degree. Okay. Oh yeah, okay. Kind of got confused. So here, the expression of U will be minus PE cos of 180 degree. What is cos of 180 degree? Yes, minus 1. So it will be PE. So this is a positive value, is it not? So at 180, it's the positive value. Correct. Kind of didn't see it right. So this is the point of maximum. These two are the point of minimum. So 0 and 360 degree. So basically it's this. 90 degree. 90 degree is over here, right? And 270 will be somewhere over here. Correct. Okay, so this is the right graph. So you can see that the equilibrium will be stable at this set of points and unstable over here. Basically, if I keep a ball over here, for example, if I just push it either this way or that way, what happens? It will just keep rolling. But here, since it's on the level ground per se, the funda is that if I push it here and there, nothing happens, to be honest. If the graph continues, it would be something like this, right? So that would be the point of stable equilibrium. Okay, guys. Now, what is that we looked at? We have seen that charges will experience force. And charges, if they're experiencing force and it's space dependent and all of that, what's happening? It'll have certain potential energy. And we're giving it a special name called electrical potential energy. So we started with a positive charge and all of that. Then we went on to take positive unit charge and so on and so forth. And we saw if we keep more than one, so we need to have certain amount of work or do certain amount of work, and all of that work gets converted to potential energy. Now we are trying to see what happens to a dipole when we keep it in a uniform electrical field. So you guys might be thinking, how is this useful? So this will help people or scientists study, or you guys study, or me study about atoms and molecules and so on and so forth. We understand the properties with all of this, how much turning happens, so how much of field it allows, and we get to know the properties. And once you understand something, then you can use it. Of course, everything is end of it commercialized or understood for better life, or of course non-commercial also. But anyways, that's the usage. There's a lot of usage. You understand something so that you can make use of it for good or bad, for commercial, non-commercial. It is left to quite a few things. Now, what did we look at? Because it's a uniform electrical field, it will experience a force which will result in zero translation motion because the forces are equal and opposite. But if the orientation is not right, it will lead to what? It will lead to rotational motion. Now things got rotated. So basically, for rotational, we need to have a torque, and in this case, we have a couple. So that depends on perpendicular distance. And we have the expression for that. And then we have the work, force into displacement. And the work for the entire journey of rotation would be this expression. So there is always standardization in physics. So in this case, we're taking the initial angle as 90 degree. And so your potential gain or loss is given by this expression. Now, this is your end of derivation, but this is to add to your understanding of stable and unstable equilibrium. So this is parallel, this is anti-parallel, and we have your stable and unstable equilibrium. So this is a point of maximum energy of the system. That's nothing but your anti-parallel. Okay. So now you guys can pause and yeah.